Okay, so yesterday done the summarization of the material like before, and I just want to do just executive summary because I think this factorization stuff can be a little bit hard the first time you see it. So the first thing to know, just to orient yourself, is that there's a theory of factorization algebras, and it's something that you don't learn in abstract algebra. So in abstract algebra, somehow the algebras and the modules and things are very static. Like you can multiply things, but here somehow the nature of the objects is that they live in geometry, right? So there's a factorization algebra on X. There's a factorization module that's all this so there's some relationship already to geometry. Kind of like Kabir was saying, maybe you picture the multiplication as kind of like, a sort of like it's just very vaguely in your head. You might kind of picture it as like you have some kind of things like this, and whenever you have a picture, then you can sort of try to maybe drag this point towards this point and then multiply it to get some kind of new picture like A1 and A2 and A3, but really the multiplication depends how you drag. And that's sort of a very, very rough picture for what it's happening in the subject, but at least it's, maybe some kind of feeling for the multiplication. Again, in real life, it's a little bit more complicated, but it's not so bad. And so the first thing I want to say is just that there exists this notion of factorization algebra. And this definition is kind of, I would say, pretty mild. So you have to deal with this Ron space stuff, but like, you saw the definition, there was this factorization condition, it wasn't so bad. It didn't look like there was multiplication necessarily built in. That you have to work a little bit harder for, but the definition, maybe it's not so bad. It's actually, just to say, it's a pretty, the thing to know about it is that even though the definition is pretty mild, it's somehow pretty complex notion. I would say in my mind it packs a punch, and and I think that part of what you're supposed to expect over the next few days is that you should get a little bit of a feeling for how it can be used in order to prove theorems. So it kind of carries some weight, and I just I'm just sort of repeating the one. Okay. Other thing that's kind of worth knowing is that this theory of factorization algebras is it's sort of equivalent with a little bit of quotes on it to the theory of vertex algebras, which I think wasn't mentioned during Kevin's talk. There's probably the theory of vertex algebras. So here, let me just say the axioms are very elementary, and they're also very they're not mild in some sense. Like they are they're it's okay. You can look up the definition if you want. And the notion, and there's theory of vertex modules and things. But you can just kind of see there the axioms are mild, but actually when you dig into it, it's pretty complex. Here you can already see I think a great deal of complexity just with your bare hands. So I think it's if people haven't seen this stuff before, it's worth going on Wikipedia on your iPhone and looking up what vertex algebras are, just to get a feeling that maybe there's some serious F in the things. And then just the only other thing I want to say, just sort of like Dennis was summarizing, just okay, so again, there exist notions, there exist various notions which you kind of a little bit follow your nose on, or you look in the origins of the subject, or you do this or that. But there exist notions of unital factorization algebra and modules. So these are like at some point maybe. There exist notions of unital modules. So often this word unital gets thrown around, and but you should kind of imagine the language is pretty flexible. The definitions are all variants on the definition of factorization algebra at the start, and that's the flavor of it. And then one of the really remarkable things is that there's, I think, two. So, okay. So the theory of factorization algebras has kind of a local part and a global part that we haven't talked about yet. But the sort of a big part of the local theory of factorization algebras is kind of given by the following two theorems, which I would say are due to Beilinson and Drinfeld. So the first basic example here is that if you have Y some affine scheme over X with a connection, this gives rise to a factorization algebra. I'm just repeating what Kevin said. A factorization algebra, which is sort of functions on Y, just call it OY. And if you take factorization modules at a point here, this is somehow approximately equal to the category of coherent sheaves on this loop space of Y. Is it Algebra Y? Is there an X somewhere? So in other words, you take this Y and lift over all of X. You take the solutions on the sections on the formal puncture disk, and this is the space of sections on this sort of puncture disk X, but space of horizontal sections. And I say roughly coherent sheaf, like this category has direct sums, and so you have kind of issues like this. But if you imagine a coherent sheaf is maybe something with finite support, then you allow unions of these sort of things. This is a precise statement it's a precise statement in various contexts and various setups. But in the original book of Beilinson and Drinfeld, which is called chiral algebras, not factorization algebras, but in their book, they explain a statement like this at the abelian category level. And there are sort of additional complications that come up in the derived category world. And one of them is that this usually doesn't really give you the derived category you wanted. So this is some kind of issue that came up in terms of T structures. So there are various corrections to this. So you work with eventually co-connective modules. Those tend to be kind of the only good ones for these factorization algebras, and you do this in co-star on the right hand side. But it's just to say this is the kind of statement you try to formulate, and then these are the corrections that you impose. And I think these technical corrections will come up a lot, so it's worth being aware of them, and it's worth understanding that like it's a little bit special. Correct, but you can kind of maybe think in these terms of the composition. And then the second statement is that if you take this Kac-Moody, okay, so there exists something which is back G kappa. So this is sometimes called the Kac-Moody chiral algebra or factorization algebra. So there's this kappa, which is supposed to be the Kabir's talk, but we all complain about it. So the fiber of this back of G kappa at a point X and X is what Kabir called the vacuum V0 kappa, which often gets written like this, the vacuum representation of this side. loop algebra, but then into this. So but really a central extension. And just like we were saying, you can ignore that for first approximation. That's another sort of technical points to be aware of, and that you'll hear more about in the next talk. And then, and let me just remind, this was the induced representation from the trivial representation. And had this extra factor that accounts for for the central. This is the vacuum representation. So, like, morally, what you should think is the formula for this vacuum representation only depends on the formal disk and the formal punctured disk. And so therefore it factorizes. So the formal disk and the formal punctured disk both are great objects that like work for this Ron blah 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 thing that you've seen. And so therefore you can really just kind of make sense of this formula over the Ron space, and you get some object which is called the vacuum representation. Sorry, the Kac-Moody factorization algebra. And then the statement is that, well, if you do this without kappa, and you take these factorization modules this point, then this is going to be a category of smooth representations of this loop algebra. So again, this is approximately, but this only really works on these co-connective objects. And with kappa, then you get modules for the central extension. And I think that there's something which is very different from the usual theory of algebras. So that maybe the first comment is that the notion of like module for a factorization algebra is much more similar to the notion of bimodule for an algebra. So there's kind of a phenomenon here in which the category of factorization modules becomes somehow much bigger than it has any right to be. So what happens here is I have this Y whose fibers are sort of sections on the punctured, on the non-punctured disk. That's like what Y is. And so this looks like something that kind of only, like in practice, what am I trying to say? In practice, this is going to look something like Taylor series. Like that might be the fibers of Y, might be Taylor series based around the point. But then all of a sudden, when you take factorization modules for functions on Taylor series, you get quasi-coherent sheaves on Laurent series. So there's somehow this phenomenon where factorization modules take something like Taylor series and produces, just taking factorization modules produces something that involves the punctured disk instead of the disk. Here, this is just like a very special module. It's not at all a compact generator for the category. Nothing like that's going on. It's just, it's, you know, like somehow half of the algebra acts trivially on the generator for this module. But then there's this miracle that, again, when you just take this certain vacuum object and you apply some functorial construction to it, then you get the full category of representations of this loop algebra. And I think that that's one of the really great, that was one of the things that really attracted me to the subject, was like, you take this sort of like big object and then it turns out it's just encoded in something much, much smaller, but with some kind of, you know, in some sense sophisticated notion of algebra structure. And yeah, but for the most part, you can sort of do the manipulations the way you expect. There are various technical issues that experts in the subject run into at different points. So you're going to see some of those things come up because experts in the subject are giving the talks. But that's the spirit of the thing. So those are my comments.
Okay. We are 17 minutes behind the schedule. So Yifei's talk will run until 4:33, and then we'll have a half an hour break. 27-minute break before lunch.
Great. All right.
26.
I know it's illegal. Can I just pause for questions? Just to see. Yes, amazing.
Is unitality a property or structure in this context?
Unitality for the algebra is definitely a structure. Let me just say property.
For algebra property, category is property.
Well,
For category, no, for category it's definitely a structure.
for a given algebra, for a morphism of algebra structure.
Yeah. Okay. Let me just say it's for the most part it's like more or less a structure. And sometimes it's possible. So
Yeah.
yeah.
About the status of the statement one is that statement is that a fulcrum or is it that definite with the definition or can you say a little bit more about
What goes into it? Yeah. Yes. So okay, so what is it like? Okay, it's I would not say it's close to the definition. I would say it's also not the Riemann hypothesis in terms of your difficulty. But what's the so it's a little bit mechanical the way you do these sorts of things. But let me just try to explain a little bit how.
So split differs until after you finish talking.
Great point. Yeah.
It's like we'll go to the
Yeah, I'll leave you there.
all right.
But you're welcome to ask questions in half an hour between the last.
Has everyone taken notes? Anyone? Okay. All right, let's begin. So, this talk and the next one will be one single unit. We will prove one major theorem, and the theorem is called fundamental local equivalence. So, I will skip writing the title of the talk.
It's another piece of chocolate.
Yes. There's a good one.
Oh,
Excellent. So the goal is to prove the following theorem. And this theorem combines every word that has been said today. So there is a canonical equivalence of factorization categories, unit for factorization categories. Between what and what. So on the one hand, we'll have the Cauchy-Long-Lustig category. I will recall in a moment what it means. At the critical level, so it involves all words that have been said today, including some that hasn't been said. And this will be equivalent to indico star over monodromy free. Or the Lagrange rule. So this equivalence is called fundamental local equivalence at the critical level. FLE, crit, as it appears in GLC2. So so let's first begin by recalling what are the two sides what do these things mean? So so first, KL of G grid is this factorization category defined to be Kac-Moody representations. So this which are integrable with respect to the positive loop group. So let me actually take a moment to explain these levels. So digression. So what do levels mean in this context? Well, so a level kappa is just a G invariant symmetric bilinear form on the Lie algebra of G. Okay, is the ground field. And given such a symmetric bilinear form, you can construct a central extension of the loop algebra, and let me do it at a point. So Kx is the local field at the point x, and here I have G hat kappa, and this is defined by a cocycle. So the central extension by a one-dimensional center is defined by the following cocycle. So that's a pairing on Gkx with itself valued in K of 1. So it sends two such elements. One is called here, so C tensor F, and one is called C prime tensor F prime, and it sends these guys to kappa evaluated at C and C prime, and then you apply the residue of operation to a certain differential one form, and that's d of f times f prime. So f and f prime are elements in Laurent series. In particular, when you differentiate, you get some one form, meromorphic one form on the disk, and you can take its residue. So that gives you a one dimension. That gives you a number. All right. So what is this particular kappa for the crit? So crit is defined to be -1/2 of the Killing form. So Goodevere didn't mention this explicitly, but everything he said in his talk about the center of the universal envelope, so on and so forth, applies to this level. Crits, in fact, they don't apply at other level, for example, 0. Yeah, so this is actually absolutely crucial in the way that we'll use Kac-Moody representations. Let me also add a small remark. So this critical level is in some sense it has been there in the subject. We could have talked about it yesterday when we even talked about 1G. So today is Moody day, but everything that's Moody today will turn local tomorrow, and so tomorrow we'll have this functor for localization. So that will go from Kashtan-Lustig, and we'll apply it to the critical level, but it will not be valued by definition in the category of D modules per se, but in a certain twisted D modules. So that there is a twisted differential operator corresponding to crit. However, geometric Langmuir conjecture, well, it's true as stated because this category turns out to be equivalent to the category of untwisted D modules. And this is because there's a certain construction for the Pfaffian line bundle, which uses this omega 1/2. But once you have this Pfaffian, the operational tensoring by the Pfaffian will induce this equivalence. And another remark that I want to make is that there is also the naive Satake functor, which was, let's say, it's an equivalence between the abelian category of representations of the dual group with D modules, but also in the abelian sense on the local hacker stack. However, if you are alert, you will wonder what happened to that funny commutativity constraint that you usually see in the proof of geometric Satake. And the answer is that actually that is absorbed by the critical level. So this is actually a symmetric monoidal equivalence, but it's only this guy that is not exactly equivalent to D mod on the local hacker stack, but only monoidal equivalent. So this actually, let me say it like this with a modified commutativity constraint. So this has always been there in the whole story. All right. So now let's turn to the other side. So the other side we have.
Maybe two remarks. So okay, so for people who don't know all the details of Satake, the type of important thing that Yifei mentioned at the end is something about some sort of dual time rule, block the order thing. Yeah, so it's important to the. And then the other thing to say is that all this half extension, this critical level, whatever, in some very precise sense, this is like if you've seen row shifts anywhere else in representation theory, it's basically just one more row shift. So it's, I think in perspective, it's fundamental, or you can do fun.
Yes. Yeah. All right. Thank you for the remark.
Sure.
Let me continue. Yeah. So the right hand side, we have seen the definition of this object, but let me just briefly summarize them in the following diagram. So we have oper G check regular. So this parameterizes your B bundle with a fixed reduction to T and a connection on the induced G bundle satisfying transversality. So this goes to I actually want to start with the meromorphic version. I want my arrow to go to the right. So this maps to the local system on the formal puncture disk, which I will denote by locus meromorphic. And there's a base change to local system on the formal unpunctured disk. So this locus is regular, and this base change is monodromy free, and this receives a map from oper G check regular, and so I will call this map I plus monodromy free, following the notation of the anyway, and I will call this map I plus iota plus. All right, so
Did I plus monodromy free or isomorphism?
no,
Great. Why did you say that?
it's not. Okay, so so because this oper G check monodromy free is in the alpha in scheme, it gives you the ability to form this category called indical lower star, and that's the right hand side. So before we start proving the theorem, let's first play around with it a little bit. Well, it's an equivalence of unital factorization categories, and part of the unital structure is that there's a unit on both sides. So what are the units on the left hand side and units on the right hand side? So units match under this FLE grid. Namely, so the left hand side is this vacuum module, G grid. So this induced representation, and this will match under the equivalence to the factorization unit there, and that object is iota plus monotony 3. Push forward, so this indical lower star category has indical lower star operation, and for this placid, so for this kind of very nice infinite dimensional scheme, it also has O. So here we have O of regular. So this is the factorization unit on the right. So if this were to be an equivalence, which it is, you should in particular obtain that the endomorphism of both sides are the same. So let's see what they are at the point. At the point on the curve, let's calculate. Well, so we know that endomorphism of this vacuum must be the same as endomorphism of this huge. This. Well, okay. The notation is huge first. I will abbreviate it. Just iota plus NF of O. Well, so in general, this end can have higher cohomology, but let's even just look at H0. So here everything is at a point. And at a point, you know what this object is. It's just induced representation. So the endomorphism between them is just you take your representation, which looks like int of the one-dimensional representation from G OX to G F grid, and then you take G of OX invariant. So it's that one, and on the right hand side, well, you're taking endomorphism of structure sheaf on some closed scheme, and this one will just give you the global section of that over G regular in the form X. So notations are this is sorry. Okay. So it tells you that this endomorphism of the vacuum at the point is actually this well, it's functions on this infinite dimensional affine space, namely the regular over. So this is in fact an integral version of a description of this center that Gerbier alluded to in his form. So this is called the Feigin-Frenkel isomorphism, maybe the integral version at the point x on the curve. So the title of the talk is actually Feigin-Frenkel isomorphism, but so well, you see that it is just a very small piece of this this huge equivalence of categories. However, the proof that these two categories are in fact equivalent actually goes in the other direction. So we'll first actually establish the Feigin-Frenkel isomorphism in a way that's stronger than what's stated here, and then we'll bootstrap the equivalence from that isomorphism. So let me say step one. Well, step one in the proof of the theorem is that we'll establish FF in the following sense. So we let Z G grid. So this is defined to be the center of the factorization algebra. Factorization algebra. This is I think it's called V G grid from Kevin's talk, and this is by definition image of that vacuum under the forgetful functor, which gives you a factorization algebra under the forgetful functor to vacuum. So one thing that hasn't been mentioned is, so there is actually an equivalence of categories between commutative D algebras. So well, commutative algebras just affine schemes over X to the 1. So there's an equivalence between that and so-called commutative factorization algebras. So whatever the center is, it's a kind of commutative factorization algebra, and we'll actually think of it as a commutative D algebra. So we'll construct an isomorphism of dx algebras, commutative dx algebras. So between ZG quid and functions on opers. Yeah, so there's a notation that I haven't introduced, but I should have. So the definition of regular opers, well, it only depends on the formal disk. So, well, another way to say it is that it makes sense as a D scheme, so as an affine scheme over X to the 1, and this is the affine D scheme that I will from now on just denote by oper to check without any declaration. There's an affine scheme over X to the 1. And just to connect this to the picture that Kevin has explained, so whenever you have an affine scheme over X to the 1, you can form two things: the horizontal arcs and horizontal loops. So if you take the horizontal arc into this affine D scheme, you'll get regular opers. Whereas if you take horizontal loops, you will get meromorphic opers. So the first step we'll do is that we'll prove that these two things are isomorphic as D algebras, and that will in particular recover this isomorphism by taking fiber at a point, and we'll recover this isomorphism by taking the horizontal loops at a point. All right, so step 2, you just
acknowledge you're right with something. Just the center is this G above there. That's the connection between the upper board and the lower.
yes, yes,
Okay.
yes.
Can I ask you a basic question?
Yes.
So, was it already explained why both sides of this isomorphism have a structure of factorization categories?
You mean this equivalence?
Yeah, why both sides of factorization?
So this has been asserted. So, well, okay. So Kevin explained to us why. So this guy is a factorization free stack. It's a factorization in the affine scheme relative to run, and in particular, in the core of it has a factorization structure.
But is it because it's like offers on some formal disk and
Right. Right. It's formed by fiber products, all of which are factorized in factorization. So that's the right hand side. The left hand side technically has not really been defined, but if you believe in what Sam summarized in that more 15 minutes before the talk started, he said this category is canonically unital factorization. And in particular, you can do this and you'll still. Yeah. But the actual definition of these things as factorization categories is actually quite important. So that's why maybe it has been hidden throughout. Any other questions? Yes.
Did we say what's the center of factorization algebra is?
Yes. Yes. So it is endomorphism so a factorization algebra gives you a factorization module. Well, technically we only define factorization modules at a point, but there's also a notion of factorization module on arbitrary copies of the curve. In fact, on anything that maps to one space. So you can regard A living on Xi as factorization module of itself, and you take its anamorphism as such. And that will give you a factorization algebra where it's classical center. So H0 of that, and that is the center.
So what is I?
So A is an arbitrary factorization algebra. Defining for as equals major K center. So in fact, I should assume that graphical. So classical not in Dima sense, classical in the sense that's not derived. You restrict to X, it's actually the part. So A of I is the pullback. So if we already something that living on the one space, we can pull back to X to the power I. That's this one. Yes, Sam, you look like you want this one.
Yeah, I want to see one more thing about Nikhil's question. So
Yeah.
Nikhil was asking the great question, why is KL a factorization category?
Yeah.
And you gave a great answer. I also want to add one more thing to give a feeling for it. So if you had taken maybe instead of representations equivariant with respect to G of O, something like representations equivariant with respect to the first congruent subgroup, that would not be a factorization category. Because that really depends on sort of knowing a point inside the formal disk in order to say first congruent subgroup. So just to get a feeling for like what's going to be a factorization category and what's not, just a good rule of thumb is that if you only say disk and puncture disk, then you're in fine shape. But if you start talking about points like Iwafori or congruent subgroups or something, then you're in good trouble. And so I think that is the counterexample also makes sense.
No, yeah, thank you. In fact, that issue will come up in just a moment. Okay. So step two, step two. I forgot what. Okay, yeah. So now, okay, so we'll construct the functor. So this will use step one, even though it does not appear explicitly. So we'll construct a functor, and this is some version of the Drinker-Sokolov reduction. So it will take the following source and target. So we'll go from Kashtan-Lustig category. My notation is not consistent. Kashtan-Lustig grid, and it will take image in Inco lower star, but of meromorphic opers. So FLE is monotropic free, but here you will land in meromorphic opers. So this will use step one. But then there's step three. So step three says that this, let me call it ds enhance. Step three says ds enhance factors factors. Sorry, I cannot write factors without assumption. Factors through and equivalence. Factors through. So this is the FLE. So it will go from Kashtan-Lustig and grid by FLE grid to this desired target and monotomy free, and it's related to the old one by I denoted the wrong nav by okay, so push forward to that target. Okay, so in fact I can cheat by not saying that because I said the factors will equivalence. All right, so step three will be accomplished in next talk, and in this talk I will only explain step 1 and 2. But in some sense, step one is already conceptually very interesting because I mean you make some construction on the G side and suddenly the dual group actually appears. So there is something very interesting about it. All right. Any other questions before we dive in?
If the right hand side is also that has
Oh, yeah. So it would just be models over this commit of. So so this guy is the one that is the state committing modules over it. That will be quantum coherent sheets on regular overs. So that will correspond to commute modules over that. Let me continue. Ah, sorry. I will not use that side because it's the afternoon.
I mean, this one, the FLE equates when over where the inside the bracket is over regular. So okay, and okay.
Yeah, then let's say it's possible.
But the way you did, while you did the rate of just that. It's one to come like this, something that's fun and amazing about the whole thing here, that like. If you ever worked with like a Verma module or something for like finite dimensional algebra, the endomorphism looks scalar. And part of what's just really beautiful here is that like you make a bunch of Verma type of things, and look at like how they map to each other, how they map to themselves. And you produce like all these big polynomial rings and how them generators, they're all kind of functions, space dimensions, really beautiful. Like it's just like it's just a fun thing about the situation. It's just really specific to the atom.
All right. Thank you. Let's construct the Feigin-Frenkel isomorphism. So this will be reduced to actually what I would call the universal case. So let me explain how this technique works. It's a general technique in this subject. So it's helpful to know. So let's consider the in the scheme version of the formal disk at the origin of A1. So this is by definition the in the scheme with K double bracket T. So I put a little hat here to distinguish it from the affine scheme version that has been appeared in earlier talks. So there is an automorphism group of this in scheme. So automorphism group of the at 0. So an R point of odd is a continuous ring homomorphism of R double bracket T to itself. Continuous automorphism of this ring. And this guy is itself a group in the scheme, but it contains as a group subscheme alt plus, which are automorphisms which preserve the base point. Preserving this, so the point 0 inside here. All right, and the relationship between these three things is that if you take so this is a group in scheme. But this is a group scheme, but it's not of finite type. So these things are related by the fact that alt quotient by alt plus is actually exactly that D. All right, so these things can be used to make universal constructions on curves. So if I take my curve x to ROM, then the observation is that this guy has a tautological alt torsor. So so this guy is by definition a point of x to ROM. So x, let me just write x in x to ROM together with an isomorphism of the in the scheme of formal disk at this point with the standard formal disk. So of course, this guy is acted on by Ott by changing this isomorphism. Now, you may wonder, can I also write an Ott plus tensor by imposing the condition that this isomorphism preserves the center? And the answer is no. In fact, because you are given a point on X the ROM, this, if you do it in family, then this guy does not actually have a section from the test scheme. So it's something that you can play with yourself. However, its pullback to X is indeed induced by from an Ott plus tensor, namely the one that parameterizes isomorphisms with fixed base point. All right, so the point is we could make constructions of those algebras. Yeah.
I remember being unbelievably pixel when first when the picture is like if you notice take K over bracket C, any automorphism of an algebra will fix the unique whatever.
Yes.
When if you place K by like K by epsilon squared,
Yes.
you make the change of variable T goes to T plus epsilon. And that no longer preserves like the center of the disk got nudged by epsilon.
Right.
That's a good
Yeah. So this is indeed. This is one way the Sam's remark came in earlier. So this we're trying to somehow say that the first confidence subgroup we cannot do this over X the ROM. So it's exactly this issue. So we can make permissive algebras which are acted on by this Ott. So let me call center G crit at standard disk 0. So I will define it to be just int of G. So this is really the standard the algebra of K, and I take G positive loop invariant, and this is acted on as a algebra by Ott. And on the other hand, I can do this for opers. So opers. Let me say standard opers. You check 0. So this is defined to be, well, it's just the affine scheme parametrizing G-check opers on the formal this. So and this is also acted on by Ott as automorphism of this D hat. So here there's a small caveat because the way we defined these opers appeals to this canonical bundle called rho of omega. And if you really want to make this precise, you actually should replace. I want something visible. You have to replace it by a double cover. Actually, a double cover over of Ott. So, namely, you need an automorphism not of the standard disk, but also of the standard square root of omega. But I will ignore this going forward and pretend it's just acted on by Ott. So now, so now the observation is that these guys are in fact just the twist of those standard guys by this tensor. So it suffices to prove to construct an Ott equivariant isomorphism isomorphism of commutative algebras between this Z G grid. Actually, let me think a bit more geometrically. Spec of Z G grid with that guy O O. So this is so this will be called, I'll call this universal case of the Feigin-Frenkel isomorphism. So let me construct this isomorphism via something called birth of overs. Yeah.
You spec on one side.
Ah, sure.
I'll beat that for you.
Thanks. So birth of overs. So this isomorphism is originally due to Feigin-Frenkel, who supplied whose argument proceeds by an explicit sort of calculation. There's nothing wrong with doing things by explicit calculation. However, there is one thing that's not apparent from their isomorphism, namely it's compatible with the geometric satake. So this is the main reason that we'll opt to use a different construction sketched by Feigin-Frenkel and completed by Sam that will render it automatically compatible with geometric satake. So this is why we're doing this. Okay, so before we start, let's first think what do we have to do. So we need to write. Well, so first let's write a map from the left to the right. So that's the grid to this scheme parameterizing overs, and this is equivalent just by the multi description of overs. This is equivalent to a G-check over. G-check over on this parameterized formal disk. So in this case, spec G grid 0 times the in the scheme. But you want this isomorphism, or you want this morphism to be all equivariant. So this data should also be all equivariant. And this odd equivariance is with respect to the anti-diagonal action on this product. Yeah. All right. So I got the other half. All right. So let's think about the general paradigm. So we want to construct something on something. So what is the paradigm? So we have, let's say, a group scheme H plus. As you can imagine, this will be our alt plus, and then we have a group, let's say, in scheme H, and H is acting on Y. And Y, for our special case, will be this affine scheme here, spec of Z. So we have this situation, then I want to construct something that is on Y times the homogeneous space, H mod H plus, but I also want it to be equivariant with respect to anti-diagonal action. So that means that I'm actually constructing something on the quotient of this thing by H. But as if you write it this way, you see immediately that this guy is isomorphic just to Y mod H plus. Yeah, so this tells you that it suffices to construct the first two pieces of data of the overs, so the B check bundle and B check the induced T bundle with rho of omega. big omega. And these guys can just be constructed over here. So one is, I think, alt plus equivariant this and that over spec z g crit standard. Now, what is the addition? The other part of the OPER data is a connection on the induced G-check bundle and the connection along the disk. So what does that mean? Well, if you think about the connection along this, what it gives you is descent data to y. And if you translate back into the language of the picture of the disk as a homogeneous space, then that's actually exactly the same as upgrading the H plus equivariance to an H equivariance. So this maps to this, and this guy is isomorphic to just H y mod H. So here, the second piece of data is upgrade alt plus equivariance on P of G check, so the induced G check bundle to an alt equivariance. So you see, interestingly, constructing an alt equivariance structure on this product is in fact easier than constructing one without alt equivariance. So it allows you to construct something just on the first component. All right, now let me give you one piece of this construction that I think is very illuminating. So namely, I will give you the
Is this PV checked? Sorry, it's just a torso for
it's a total for B check.
B check.
Yeah. Yeah.
Where does maybe means this? Where does the local structure come?
Yeah. So what we wanted is we wanted the P B check on this So yeah, it says something in words, but so we want PB check and this structure over here, and then we wanted a nabla on the induced G check bundle, right? And I claim that that nabla on the G check bundle is exactly descent data of the G check bundle to here. And now this means that I just need to upgrade my H plus equivariance to H. But then, of course, there's an upper condition that you still have to check, but you can formulate it in terms of the what happens on this y times the disk. All right. Yeah. So let me give you one piece of this. Namely, let me give you the bundle, the check bundle over. So this will be P B check G check. So this is the first thing that you actually construct, and then you show the passive reduction to B and so on and so forth. So what is this B G check bundle? Well, let's take the Tanakian perspective. All I need to do is that I need to give you a tensor functor from representation category of G check to modules over this algebra mod. So what is this functor? It sends so here is where the dual group creeps in. So it will always creep in via geometric Satake. So it will send V to the naive Satake functor applied to V. So here it's very important to actually think of this as critically twisted demodule on Rosmanian. And now what you can do is you can forget it into a unit coherent sheaf of the affine Gauss-Bonnian. And now you can take global section, and after you take global section, it's going to carry a structure of a GK module. So it's going to carry a structure of a object in Gaussian-Lustig category, and in particular, you can take G the invariance. So that is the module. So it actually takes some effort to show that this operation actually gives you a well-defined thing. For example, this global section is actually concentrated in degree 0, and so on. But this is proved in science theorem, a science paper. That geometric proof of Feigin-Frenkel isomorphism, which I recommend. All right.
Maybe just to say because like it's just part of what's going on here is you think the global sections are some packages. Like you literally just get this the vacuum direct from itself a bunch of times. So when you say that more canonically, what that multiplicity space is, it is like central fiber style.
So yeah, in fact, one can make a small but important remark as we just see. So if I take, well, it has to be a symmetric monodal functor, in particular should take the symmetric monodal unit to this algebra. And why does it do that? Well, you take your one-dimensional representation on the naive subtract, it becomes delta function of the one section. And if you think about it as a twisted D module, and then you take its global section, then you will get exactly the induced representation. All right. Okay. So why am I telling you this? So I want to state a consequence of this construction, which will be used. Consequence of the construction, which will be used later on. Taking some of the upshots of the Berthold-Opper construction, namely, it tells you that this vacuum representation has a Hecker eigenproperty with respect to the convolution action of the spherical subatomic category. So we think conform with this one, who is isomorphic canonically to V. So V can be thought of as a quasi-coherent sheaf on locus regular, and you can pull it back to Opper. So now you can cancel with Opper. Functions over Opper. G reg. And this acts as endomorphism of the vacuum, so you can cancel it. So this is by Feigin-Frenkel. So this is the sort of the fact that is really at the heart of Feigin-Frenkel's construction of Hecker eigenscheme. So with this Hecker eigenproperty of the vacuum. Yeah.
But you get why that gamma equals GT invariant gives you an object. So why is it a representation of?
Yeah. So that's a general general fact. So I mean, if I have if I have a D module on a homogeneous space H mod K, then if I take its global section, then it will have an action of the Lie algebra base by that by embedding as vector fields. And now if this object is K integrable, then the result will have the structure of a K module. So that's why it's an object of KL.
If this construction was important, would they create it just the D modules was and why?
Like if you were at another level, then like it wouldn't be the case that you involve shit a bunch of conflict back. The set of factors.
Yeah. So the consequence of the constructed group. Yeah, I mean, so just on a very basic level already, this functor uses Naive which lands in critical twisted models.
Okay, so that's the
Yeah, that's actually a non-dimensional model.
No, but like a simply connected group is still fine, it's still the other problem. Those vacuum objects, the only time it's heterogeneous, right, first of all.
I actually didn't hear exactly what you said. But maybe let me continue and then maybe we can talk after. I don't want to delay everyone's
Sorry, now that we seem to be done with step one, like ultimately we want an equivalence category, so far we have an isomorphism of algebras. What's the relation of like they're the centers, or like what's the relation of these algebras for
the category. That's the thing that I explained at the beginning. So you ultimately have this equivalence of categories, right? So you take vacuum on both sides, you take H0 of endomorphism. And that's this.
okay. But we will prove it first.
No, we already. No, yeah, we will prove this first and then we do this. But we already did step one.
Yeah. But,
Yeah. Okay, so we declare step one to be done. Even though I only give you one piece of it. But let me also say something about step two because it's important. All right. So step two involves a crucial new ingredient that will also feature later in later talks, which is the so-called affine Scriabin theorem. Due to Sam Ratkin. So what does this theorem say? So the theorem wonderfully it actually applies to all levels. So it says the following. So if you consider this Feigin-Frenkel functor ds from G at kappa mod 2 vex. So this is the functor of semi-infinite cohomology on loop algebra for n with this Whittaker twist. So it could be explained it, and I think in one of the future talks, a more precise definition will be given. I think, yeah, or yeah, I don't know. All right. So the theorem states that this functor induces an equivalence of factorization categories that we call DS enhanced from the Whittaker coinvariance. So whenever you have a category acted on by the loop group, it makes sense to perform this option, this operation. And it showed up already in Andrea's talk for the special case that this is the modulus on the affine Riemannian. So it asserts that this guy is equivalent to ds applied to the vacuum kappa. So this has a structure of a factorization algebra. So it's a general paradigm. You have a what's so-called lax unital factorization functor. It will always send the unit to a factorization algebra, and it will induce a functor from the source to factorization modulus over that factorization algebra. And this is almost an equivalence up to this funny procedure that I will denote by renormalization. This procedure that Sam sketched at the beginning. So maybe let me say one word about 1 minute. So let me say one word about what is happening. So at the point I infer, what is happening is that this left-hand side is equivalent to co-limit of a bunch of categories. And here, so each of which, so each with up to n is generated by a single object. By a single object. Let me call Wn kappa.
So, it's time is very short. You don't need it. I'll do it myself.
Okay, sure.
If you don't need DS from which start, just go from Kasmudi. Let's just save time.
Sure.
Yeah.
But I'm not sure if this is the one that causes the. I mean, let me just okay. I will take at most 1 minute. I mean, okay.
You see, we didn't introduce what we started. We didn't introduce the categorical. It's like.
Okay. Yeah. Okay, so let me. Okay, I was going to tell you a bit about this, but let me skip this conversation then. And so let me say one thing particular about critical level, which I think you will need. Okay, one thing particular about the critical level is that it's crit. This ds back is isomorphic to this Feigin-Frenkel center as a factorization algebra. So this is the affine analog of the result that Vermeer explained at the very end. So which in the finite case due to constant theorem. And this, if you recall, by Feigin-Frenkel is O of G check regular. And the combination of these two, this observation with that equivalence is that, well, okay, let's not talk about the width star then, is that we have the functor ds going from G at grid mod all the way to factorization modules for this guy, which is actually has to do with meromorphic opers. And this renormalization procedure exactly yields the category integral upper as lower star.
So I mean, let's emphasize this is exactly why Karen gave this talk.
Yes.
So like the fact that these factorization modules give the star is that was the purpose of
Yes.
the talk.
Yes. So let me just say yes. In Kevin's talk, the following thing appeared: op G regular O mod fact receives a functor from this thing on the top, which is an enhanced version of global section, and this is equivalence on eventually co-connective parts. And yeah. Anyway, I will stop here. Oh, sorry, I cannot stop here. Sorry, I didn't. Yeah. Sorry. Yeah, Dennis, you derailed me. Okay, so so the desired functor that I promised you in step 2, which is written there, is going from KL G crit, which is by definition G check crit mod L of G forgetful to G crit mod composed with this this functor ds enhanced. Okay, and in the next talk, Dennis will explain why this factors to the desired equivalence FLE. Thank you very much.
X up to 5, we can't delay, but we have enough interrogation time for Yifei and Zhao. Do you understand?